Okay, here goes. Just as a reminder, sort of the framework for our problem solving is Polya's 4 steps from his 1945 book. And those 4 steps are: understand the problem, make sure you have an idea of what it is you're being asked, devise a plan, figure out how am I going to go about solving this problem, carry out the plan, go ahead and do it, see what you get for an answer. And then finally, and a really important step here is look back, make sure your answer makes sense. If you were given instructions on how to round, make sure you rounded to the appropriate place value, that kind of thing. So don't forget that look back. That's a really important part of the problem solving steps. Let's take a look at a problem that's a little new for us today. A frog is climbing out of a well that is 8 feet deep. The frog climbs up 4 feet per hour, but then has to rest for an hour, during which it slides down 2 feet. How long will it take for that frog to get out of the well? Some of you may do this just with numbers and write down where the frog is. He climbed up 4, then he slid back 2, so he's at 2. He climbed up 4, so he's at 6. Nothing wrong with that. I think for something this visual, though, I'm going to use a picture. And so I've got my frog, and it's climbing up. And the well is 8 feet deep. I'm going to keep that in mind all the way through the process. So I've understood the problem. Frog needs to climb up to 8 feet. I've devised a plan. I'm going to use a picture. And now I'm going to put that plan in place. So he climbs up 4 feet. So that's where he is. But then he rests for an hour. So he slides down 2 feet during his second hour. Oh, and you can put as many notations on here as you need to make sure that you're keeping track. So if you wanted to put a 1 down here to say that's the first hour, he climbed up 4 feet. And then during the second hour, he slid down. Let's see, when he slides down 2 feet. So now he's at 2 feet from the bottom. Okay, then he's going to climb up again. He's going to go up 4, so that's going to put him at 6 feet. It's been 3 hours. But then he's going to slide back down to the 4-foot mark, and that's the 4th hour. And then he's going to climb up 4 more feet and get to 8 feet. That's the 5th hour. And it's 8 feet deep. He made it to 8 feet. He's out of the well, and it took him 5 hours. You could do this by writing down numbers and not with a picture. I really like the picture method. We kind of saw that with pigs and chickens on Monday. If you have questions about this, let me know. Otherwise, I'm going to have you try one that's similar. Okay, here goes. Frog is climbing out of a well that's 11 feet deep. He climbs up 3 feet per hour, but then has to rest and slides down a foot. How long will it take for this frog to get out of the well? I'll make a poll for this and let you try it. And these are in hours. So we're not going to take minutes into account here. It's just hours. How many hours will it take this frog to get out of the well? And if there are folks that weren't with us on Monday, essentially what we're doing with the poll here is you should see a list of multiple choice answers pop up on your screen, and you just choose the one that you think is the correct one. Polls like this are a chance for you to find out how you're doing on the types of problems you can expect to see in our practice problems, in assigned problems from the book, on quizzes, on exams. And if you're doing really well while we're in class, then you're probably going to be in pretty good shape when you go to work on the practice problems, which means you're probably then going to be in good shape for the quizzes. If you run into trouble or you have questions you want to ask, this is a perfect time for that. Also, these polls give me information on how is the class doing with this type of problem. If it's a real struggle, then we need to spend more time on it. If for the most part students are comfortable, then I feel good about go ahead and move to the next thing. Let's go another, I don't know, 25 seconds, then we'll do this one together. All right, let's see how we did. Okay, not unanimous, but strong agreement. That's where most of our polls will tend to come in, and this one's no different than that. So let's go ahead and take a look at it. One thing I will say is, if you didn't draw a picture and you think a picture might help you, then I would encourage you to draw the picture. And so let's see here. It's an 11-foot deep well, and it climbs up 3 and slides down 1. So the frog climbs up 3, puts him at the 3-foot mark, slides down 1, he's at the 2-foot mark. Goes up 3, that puts him at 5 feet, slides down 1, that puts him at 4 feet. Climbs up 3, that puts him at 7, slides down 1, that puts him at 6. Climbs up 3, that puts him at 9, slides down 1, he's at 8, and then climbs up 3 to 11, and he's made it out of the well. Now, I didn't label those at the bottom, but I can go back through and just count them. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 hours. So it took 9 hours for that frog to get out of the well. That was our most common answer, which is great. If you have any questions you want to ask about this one, please don't hesitate. All right, let's try something different. A student has 8 coins with a total value of 50 cents. What are the coins? So here, we could think about the coins that are possible, which would be to get up to 50 cents, you could have pennies, nickels, dimes, quarters. You could say $50. The thing is, the student has 8 coins. So $1/2 would be 50 cents, so that's not going to do it. We could kind of trial and error this thing and do maybe 2 of each and see what happens. That's one way to go, is you could say, well, what if he just has 2 of each? Let's see, the pennies then would be 2 cents. The nickels, 5 cents times 2 would be 10 cents. The dimes, 2 times 10 would be 20 cents. And the quarters, 2 times 25. Oh, you know what? 2 quarters already puts this student at 50 cents. So that's not going to work. That's no good. So 2 of each is no good. Okay, well, maybe I trial and error this a different way. And I say, let's just say they're all nickels. That'll keep them under 50 cents. So if they're all nickels, then we have 8 coins. They're worth 5 cents each. That's 40 cents. It's not correct, but we're in the ballpark. Basically, I just need to bump this up a little bit. What could I do by changing those coins a little so that instead of 8 nickels, I have something else that gets me to 50 cents? What would I do with those coins to change it so that this works and I have 8 coins that add up to 50 cents? And there's a couple ways you could say this. You could say what the answer is, or you could say what you need to trade. Clearly 8 nickels won't work. So I need to get rid of some nickels and replace it with something else. Yeah, Jalen, go ahead. You can either type it or you can turn on your microphone. That'd be just fine.
Could you do 6 nickels and 2 dimes?
Well, let's take a look. Trade him for dimes, Sergio says. Okay, so You and Jalen are in the same place. All right, let's see. So I'm going to take two of those nickels and trade them in for dimes. So I'm going to have 6 nickels, 2 dimes. So now I have 30 cents in nickels. I have 20 cents in dimes. Sure enough, that's 50 cents. So that meets this part of the problem. And I've got 6 nickels and 2 dimes. That's 8 coins. That meets this part of the problem. And that's exactly where we land. 6 nickels and 2 dimes is how we'll get there. If you're thinking, could I do something other than trial and error? Well, this is one where you could kind of draw a picture the way we did with our pigs and chickens. And you could say, all right, I'm going to make these all nickels. They're all nickels. But that's only 40 cents. So what if I trade out one of those nickels for a dime? Okay, now I have 20, 30, that's 45 cents. So I'm not quite there, but I'm closer. I'll trade another nickel for a dime. And now I can see I have 6 nickels and 2 dimes, 8 coins, 50 cents. So you can do this with a picture. You can do it with trial and error. Not sure there's really an algebra way to go about this one, but just because there'd be so many variables involved. But this way absolutely works. I'm going to have you try another one. It's not going to be exactly like this. So a little creativity might come into play here. That's something that sometimes is frustrating for students in this section is sometimes there's a little creativity involved. We'll try to stick with a similar theme with our problems, and what you see in practice and what you see on quizzes is what we've grown comfortable with rather than throwing something totally new at you on a quiz. I wouldn't think that would be right. But when we're doing this and when we're doing practice problems, I think being a little creative is a good thing. All right, here goes. Or being forced to be a little creative is a good thing. Here goes. Matt has 9 coins. None of them are dimes. He has at least 1 penny, 1 nickel, and at least 1 quarter. He has more nickels than pennies. He has 3 times as many quarters as nickels. How much money does Matt have? I'm going to make a poll for this. And one little hint I'll throw your way is you've got to figure out how much of each coin he has to figure out how much money he has. Trial and error is valuable here. Writing down what you know is really valuable here. I don't think these questions like this are easy. They read like they should be. And then we start writing stuff down and I'm not sure exactly what to do. Basically, take advantage of what you know and then work from there. And then I guess pennies are worth 1, nickels are worth 5, quarters are worth 25. Make sure we use that when we go to get our final answer here. All right, let's go another 30 seconds on this, and then we'll talk through it. A couple of things about the polling. If you get an answer that's not there, you don't see it, pick the one that's closest to yours, then I'll know you've had enough time to finish it, and then we can talk about it and try to clear up any misunderstandings you might have had. And if I say we're going to take 30 more seconds and you need more time than that, it's okay for you to pop up a message in there and say, hang on a second, I'm not quite ready yet. That's fine. And if you're not quite done and you don't need to say, I need more time, you can just keep working on it while we talk through it and then see if your answer matches the one that we come up with. All right, let's see how we did on this. Okay, strong agreement. Little disagreement there with the $1.57, but mostly strong agreement on the $1.61. All right, so let's take a look at this one. What we're looking at here is, let's see, 9 coins. None of them are dimes, so he only has pennies, nickels, and quarters. I suppose he could have half dollars, dollar coins, but he's got at least 1 penny. Okay, so he has at least 1 penny, at least 1 nickel, and at least 1 quarter. So we'll just start there. Now that's not 9 coins, so we know that's not the right answer, but we can start there with 1 of each because he has at least 1 of each. He has more nickels than pennies. Okay, so maybe instead of 1 nickel, he has 2. That would be more than the pennies, and 3 times as many quarters as nickels. Well, if the nickels is 2, and I may not be right about that, it might be 3 or 4 or 5. I just know he has more nickels than pennies, but if it's 2 and he has 3 times as many quarters as nickels, then that means he's got 6 quarters. 2 times 3 would be 6 quarters. And now we've got 1 penny, 2 nickels, 6 quarters. That's 9 coins. That's exactly what we were after. So we just need to figure out how much money this is. What we want to do here is make sure we satisfy all the conditions we're given in the problem. 9 coins. We have 6, 7, 8, 9. Okay, that's satisfied. At least 1 penny, at least 1 nickel, and at least 1 quarter. Yep, we've got that handled. More nickels than pennies. Yep, we've got that. 3 times as many quarters as nickels. Yep, we've got that. We've satisfied all the rules I was given, and we can see that there are 6 quarters plus 2 nickels plus 1 penny. And we'll add those together. Let's see, 6 quarters, that's $1.50. 2 nickels, that's 10 cents. And a penny, 1 cent. Adding those together is $1.61. If that didn't clear it up for you, if you have questions you want to ask, please let me know. Not everybody answered the poll, so if you have questions, it's okay to throw those my way. Perfect, Sergio. That's what we're after. Outstanding. Very good. Very good. Okay, here's something a little different. A train leaves North Platte, Nebraska at 6:05 a.m. Central Time heading west. It stops in Salt Lake City for an hour and 40 minutes and then continues on to Elko, Nevada, arriving at 5:55 p.m. Pacific Time. For how long was the train actually traveling? So we want to make sure we make sense of this thing. Okay, so got this train and it's here in North Platte, Nebraska, and it goes west and it stops in Salt Lake City for a little while and then it continues west to Elko. I don't want to count the time it was stopped, and I want to know how long did this journey take? One key hiccup here is it left Nebraska at 6:05 a.m. Central Time, which it would, and then it arrives in Elko, Nevada at 5:55 Pacific Time. So we're not working with the same time zone, so we can't just look at, well, 6:05 to 5:55, whatever that is, we got it. The key here, if you see a problem like this, a key is make sure that you work in one time zone. It doesn't matter which time zone you pick. Just make sure you're working in the same time zone for both locations. I think I'll just, since it ends on Pacific time, I'll just use Pacific time. It would be fine if you wanted to use Central time here, that's okay. I'm gonna go ahead and use Pacific time. And what I'm gonna do there is, well, Central time is, let's see, there's Eastern, Central, Mountain, Pacific. So Central time is 2 hours ahead of Pacific time. What that means is this train left North Platte, Nebraska at 4:05 a.m. Pacific time. Because Pacific time is 2 hours earlier. So when it's 6:05 Central time, that means it's 4:05 Pacific time. And now when I look at my timing here, that train left at 4:05 a.m. Pacific time. It arrived at 5:55 p.m. Pacific time. So from 4:05 a.m. to 5:55 p.m. Let's see. You can count that however you want to. I'm going to use my fingers. So let's see. It left at 4:05. And you can't see it, but I'm counting on my fingers. 5:05, 6:05, 7:05, 8:05, 9:05, 10:05, 11:05, 12:05, 1:05, 2:05, 3:05, 4:05, 5:05. So I've got 13 hours gets me to 5:05 p.m. And some of you might say, well, 12 hours makes it 4:05. Another hour makes it 5:05. So that's 13. And I don't want to try to use my fingers. Totally fine. And then let's see, we're at 5:05. We still have another 40 minutes to go. Or no, 50 minutes to go. Sorry about that. So that's 13 hours and 50 minutes. But be careful. Oh, good, Laura. Be careful. Remember, the train wasn't going the whole time. It stopped in Salt Lake City for an hour and 40 minutes. So while the whole journey was 1350, all right, Katrina, that we need to subtract 1 hour and 40 minutes because it was stopped for that long. And when we do that, we end up with a total traveling time of 12 hours and 10 minutes. I think these questions are kind of cool. I like the opportunity to count on my fingers. And if you wanted to do this all in Central time, you could. The train would just arrive in Elko at 7:55 Central time. And then you'd count your time the same way. You'd have 1350 and then back off that 1 hour and 40 because it was stopped for an hour and 40 minutes. Let me know if you have questions on this before we talk about the next thing. Okay. Even and odd models. This isn't something we'll spend a ton of time on, but I want you to be aware of it. There's a way that we can model even numbers and odd numbers. And a key here is that an even number is always a multiple of 2. If we think about the even numbers, 2, 4, 6, 8, and so on. Every even number is a multiple of 2. 2 times 1, 2 times 2, 2 times 3, 2 times 4, and so on. So every even number is a multiple of 2. So a way for us to draw an even number, just any random even number, is with that, a bar like that, and a bar like this. Because what we're doing is we're saying, whatever this thing is, if we double it, it's an even number. You'll notice this even number doesn't have anything hanging off the sides. It's perfectly even. What I mean by that is it's over here and over here, there's nothing sticking off the edges. That's an even number. If this even number is 2, then it's a 1 and a 1. If this even number is an 8, then it's a 4 up here and a 4 down here. And so we're just using a block to represent even number. I'm probably talking about that more than I need to. Most of you are probably like, yeah, I get it. Okay, sorry. So if we're going to model an even number that way, how do we model an odd number? Well, an odd number is really, let me label that one as even. If we're going to model an odd number, then an odd number is really just going to be if we make an even number, whatever that even number is, and then we add 1 to it. Now it's an odd number. Now it's not whatever this is times 2, it's whatever that is times 2 plus 1 more. 2 times 1 would be 2, add 1 on, that's 3, that's an odd number. 2 times 4 would be 8, add 1 on, that's 9, that's an odd number. So that little this little piece hanging over the edge makes it an odd number. And then if I want to make some kind of generalization, like if I add an odd number to an odd number, so odd plus an odd, what kind of result must I get? If I had an odd and an odd, what do I get? Every single time. Great, Laura, you're exactly right. There's a couple ways to answer a question like this. I'm kind of doing it with this model here. Very good, Sergio, Katrina, Lee. And if anybody wasn't here Monday or didn't get to hear it, the more people that type it in, the better, because that's me looking around the room, seeing a whole bunch of hands go up. So I feel like, okay, we're all on the same page here. I'm doing this with a model where, okay, that's what an odd number looks like. And now I'm going to put another odd number over here. And if I were to connect those two together, if I were to push those together, what I end up with is an even number. So you could do this totally with a model, with a generic situation where this is what an odd number looks like, this is what an odd number looks like. And if I put those two puzzle pieces together, now I have something that's an even number. You could also do this. Oh, good. Thanks, Laura. Or you could just, if a question comes up and it says, what do you get when you add an odd to another odd? You can just try it. Well, if I take an odd number and I add an odd number, I get it even. Okay, it worked on that one. I'm not totally convinced. How about if I take an odd number and I add an odd number, I get, yep, every single time I add 2 odds, I get an even. And you can absolutely do it in a concrete way like this, or if this model here makes sense, fantastic. Also, it's a way for me to show you how we do model even and odd numbers when we want to draw a picture of just a generic even or a generic odd. Up next, we're going to look at some patterns. If the following pattern continues, what letter will be in the 50th position? And so what we have here is baseball, baseball, and the idea is it's going to continue. Baseball, 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 baseball. And we want to know if that continues, what letter is going to be in the 50th position. You could do this with brute force and just keep writing the word baseball down over here and count until you get to the 50th. But I don't think that's the best way to go. I think it's probably better to come up with some kind of a plan that's a little more efficient than brute force. Joanne says, hey, already got an answer for us. Yeah, that could be true. I'm not sure yet. Let's see. And Joanne, if you want to tell us what you did, I'm open to it. And I never want to put anybody on the spot like this. If Joanne, if you want to say, it's too hard to explain, I can live with that. If you want to tell us what you did, I think that's great. Especially early on in the semester, I definitely don't want to put anybody on the spot. Later on, when we're all more comfortable with each other. 6 times 8 equals 48. Lee agrees with Joanne. Oh, don't worry about it, Will. You're good. All right. So let's see if I can piece this together. Joanne, you tell me if I'm incorrect. What you did was said, if I look at this word, there's 1, 2, 3, 4, 5, 6, 7, 8 letters in one little group that's baseball. I'm trying to get to the 50th letter. So what I'm going to do is I want to get to 50. I'm going to divide that by 8 and see what I get. Now, maybe Joanne just multiplied and didn't fool with this division part at all, and that's okay. Remember from yesterday, there's more than one way to do a problem, and that's all right. But if I do 50 divided by 8, I get 6.25. Now, this is a little bit dangerous in a problem like this, because in a problem like this, we absolutely do not care about what's after the decimal point. Things will get goofy if we look at what's after the decimal point. The key here is just focus on that whole number part. What that means is this word is going to appear completely, fully, 6 times before we get to number 50. And then this is where Joanne's comes in. Okay, it's an 8-letter word. So if I do that 8-letter word, 6 times, then I'm at 48. So I'm going to do this, and there's 8, 16, 24, 32, 40, 48, and I'm still trying to get to 50. And so this would be 49, and this A right here would be 50. Basically, what I do with the division step is this tells me how many full baseballs there are going to be, and then I'm essentially starting over at the beginning. If I'm at 48, I still need to count 2 more to get to 50, and that's how I can figure out that this A right here is baseball. All right, Katrina, very good. 10th letter would also be in the 50th position. Since there are 8 in the starting word, I'll agree with you on that. Won't always be true for every word, but since there were 8 in the original word, I would agree with that one. Okay, so let's have you try one like this. Same word. What letter will be in the 326th position? I'll set up a poll for this and let you try it. I used a capital L there, not to be tricky. It's just I wanted to make sure it didn't look like a 1. I wanted to show up correctly as a L. Oh, you might not see the lowercase. They might all come up capital letters. As you saw when we talked through the last one, there's more than one way to go about answering this question. 326 isn't a number that we use that often, so it's one that's a little harder to jump right to than 50, but there are definitely different ways you can get there. We'll go another 30 seconds and then do this one together. All right, let's see how we did. Okay, not unanimous, strong agreement. That seems to be our sweet spot. That's really good though. So let's take a look at this. Okay, what is in the 326th position because we did it just a minute ago, I know that there's 8 letters in the word baseball. So we're going to start out with 326 divided by 8, and that'll let us know how many full baseball words we're going to have in trying to get to 326. It's like 40.75. It's really important here to throw away the remainder. If you look at that and say, well, there's 40 full ones, and I'll just go 7.5, we'll call that 8, then you're using this decimal part incorrectly. We'll talk about other number-based systems later in the semester, but that decimal is not an indicator of where our letter is going to be. What we get here, though, is we're going to have 40 complete baseballs as we work our way towards 326. And when we do 40 times 8, that'll be 320. So the word baseball is going to end at number 320, and now I just need to count the rest of the way to 326. And there's 321, 2, 3, 4, 5, 6. It's actually the second A in baseball that we land on this time, but sure enough, in the 326th position is the letter A. Let me know if you have any questions on that before we look at something a little different. One thing I like about today is there's a wide variety of questions for us to play around with. Okay. Here's one that reads a lot more complicated than it is. When items from a box are placed into groups of 3 or into groups of 7, there's always one item left over. What's the smallest possible number of items that are in this box? Okay, that one reads a little strange, so let's take some time and make sure we understand our problem. We've got this box, I don't know, say there's Legos in there, or toy cars, or whatever it might be. And when we try to put whatever's in that box into groups of 3, there's always one left over. And if we try to put them in groups of 7, there's always one left over. What is the smallest possible number of items that are in this box? Okay, the way we're going to approach this, it's going to be a trial and error situation, but we definitely have a strategy. So I know I want to have one item left over. So I want to make sure my answer is 1 bigger than a multiple of 3. It also needs to be 1 bigger than a multiple of 7. We're not going to talk about greatest common factor, least common multiple just yet. For right now, I need a strategy here. And okay, well, I have to have a remainder when there are of 1 when there are 7. So maybe I could have 8 items. If I have 8 items, if I make groups of 7, I have 1 left over. Because 7 go in a group and there's still 1. If I try to make groups of 3 here, though, I'll have 3 and then 6. I have 2 left over. So that doesn't work. So 8's no good. All right, well, let's try the next thing. I like it, Jalen. The next thing would be, okay, well, 8 didn't work. What's the next thing with 7 that I could try? Well, 7 times 2 would be 14, so maybe 15 works. That works for my group of 7. But if I have groups of 3, I'm going to go 3, 6, 9, 12, 15. I'm going to have 0 left over. So 15 doesn't work. And then good word, Jalen's a little on the ball there with the 22, because that's going to give me 1 left over for my 7s. And if I have groups of 3, 6, 9, 12, 15, 18, 21, 22, there's 1 left over. And so 22 is the smallest number of possible items in the box. There are other answers that would be correct here that are bigger than 22. So the fact that this said what's the smallest possible number of items in the box points us to just 1 correct answer. Let me have you try one that's similar. When items for a box are placed into groups of 4 or 6, there's always 1 left over. What's the smallest possible number of items in the box? I'll make a poll for this and let you try it. And here it is kind of trial and error, but it's trial and error with a strategy, kind of like we did with the coins. That was a trial and error, but we had a strategy there. We didn't just do it blindly. Go another 30 seconds on this one, and then we'll talk through it. All right, let's see how this one went. Strong agreement on 13, but also some other ones that one of those I'll talk about for sure. All right, so as we look at what we've got here, when items are placed into groups of 4 or 6, there's one left over. We're going to start with the larger of those two numbers. That's going to be our driving force here. And we're going to say, well, I need one left over from 6, so I'm going to try 7. And as far as 6 go, I have one left over. As far as 4 goes, well, I'd make a group of 4, and then I would have 3 left over. So that didn't work. So 7's no good. Okay, well, 6 times 2 would be 12, so I could try 13 here. And with 13, 6 times 2 is 12. There's going to be one left over. And 4, 8, 12. Look at that. There'll be one left over. So sure enough, 13 is the smallest possible number of items that are in the box, because if I have 13, I'm going to have one left over, whether I make groups of 4 or groups of 6. There's a strong pull here to want to say 25, and I totally understand it. You look at these two and you go, well, 6 times 4 is 24. So I know 4 goes into 24 evenly, and I know 6 goes into 24 evenly. So if I just add 1 to that and use 25, then I'm going to have one left over. And you're right that there would be one left over for groups of 6, and there would be one left over for groups of 4. The kicker here is we're looking for the smallest possible number, and it happened to work at 13. So while I think this is a nifty little shortcut, it doesn't always give us the smallest possible number. Let me know if you have any questions on what we did there before we look at a different type of question. And I do sort of get a kick out of all the different types of questions we get to work with in 1.1. Oh, very good. Awesome. All right. A classic car show has 4 entries, and 81 people will vote to select a winner. What's the smallest number of votes possible for a car to be declared the winner? Now, your first thought might be that, well, there's 81 people, so there's 81 votes. So if you cut that in half, that's 40.5. So if you get 41 votes, that would make you the winner. Yes, Denise, that's right. There's one left over if you make groups of 4, one left over if you make groups of 6. That's how that problem was set up. And 41 votes would definitely make one of these cars the winner. But here, kind of like the last one, it's not just how many votes would make you the winner, it's what is the smallest number of votes possible for a car to be declared the winner. You'll see at the top here, it's called pigeonhole remainder. The last question we did was kind of a remainder question. There's a pigeonhole thing because we're making groups. So we're putting these things in these places and seeing what's left. Something didn't fit in the pigeonhole. There was one left over. Really, those last ones are remainder more than pigeonhole. This is sort of a problem that relates to something called the pigeonhole principle. I'm not going to ask you that, But that's why that title's up there at the top of the page. And you'll see how this works like pigeonholes in just a second. So there's 4 entries in this car show. I'm going to call them A, B, C, and D. You can be more creative with those names if you want to, but those are the cars. And there's 81 people that are going to vote. So let's just say they all get the same number of votes. Well, it's going to look a lot like our pattern recognition thing with the baseball. If I take those 81 votes and I divide it among the 4 people, let's see, 81 divided by 4, everybody gets 20.25. Well, you can't get 0.25 votes. Excellent, Sergio. So I'm going to give everybody 20 votes. And so those 20 votes, those are like pigeonholes. 20 pigeons went in this hole, 20 pigeons went in there, 20 pigeons went in there, 20 pigeons went in there. At this point, I don't have a winner, but I still have a vote out there to go because this is 80 votes. So I still have 1 to go. Perfect, Will. So if I just give that to car number 1, the A car over there, 21 is the smallest number of votes possible to be declared the winner. So the smallest number of votes you could get and win is 21. It's got more than everybody else. It adds up to 81 total votes. So that's how this could work, and you could get 21 votes and be the winner. Let me have you try one. This classic car show has 6 entries and 200 people will vote. What's the smallest number of votes possible for a car to be declared the winner? This one is a little bit more challenging than the last one. Not a lot, but a little. You have to be careful. I'll set up a poll for this one. We'll go another 30 seconds, then we'll talk through this one. That's okay, Brianna. This is the last thing we're going to do today before seeing if anybody has questions. So as far as new content goes, I don't think you'll miss a thing. Thanks for letting me know. I appreciate that. All right, let's see how we did here. Okay, mostly 35, a lot of 34. And I understand that. That's sort of, if you want to call this a trick question, I wouldn't. But if you wanted to, you might say that it's a little bit of one. So let's see here. Our classic car show has 6 entries. So we have A, B, C, D, E, and F. Those are our pigeonholes. we're going to start putting pigeons in there. We have 200 people voting. If we divide by 6 so that everybody gets an equal amount, that's going to be 33, and this decimal part doesn't matter. So everybody's going to get 33 votes right out of the gate. At this point, you might think, well, if I just give A 34 votes, then that's how many it needs to win. But let's make sure we've got all our votes here, because there's 200 votes. And at this point, we have 33 times 6. Let's see, 33 times 6. 33 times 6, that's 198 votes. So I still have 2 votes left. Then the 2 votes is a little bit tricky because I have to figure out, okay, wait a minute, where do they go? Because if I give A a vote and B a vote, now I don't have a winner. Oh, so the only way this works is if both of these 2 votes go to the same place, A gets 35 votes, and now A's our winner. Because if I give 34 and 34, I don't have a winner. In order to have a winner, both of these votes have to go to the same place. And so the smallest number of votes that would guarantee a win is 35. I guess it's kind of a trick question, but not really. You just have to make sure once you've put all these votes in place, how many have I accounted for so far, and then make sure that the rest of them get spread around in the way that makes it, yeah, that's true, that makes somebody your winner.